Now I lied and I said we were going to go over a coding example, but I forgot. Let's do the F distribution first, and then we'll go over a coding example because it's very related to what we just did with deriving the t distribution. So I'm going to take a simple example, and I think you should be able to extend this to slightly more complex settings. So consider testing the hypothesis that h naught k beta is equal to 0. So now we want a hypothesis test where k is a full row rank matrix. So it's some number of rows and then peak columns, but it's at least a full row rank. And so because we want to test a vector, we can't use a t-distribution or a univariate t-distribution, so we need to use something like an F distribution. Our natural estimator of k beta is k beta hat, which under our standard assumptions from this section is going to be normally distributed with mean k beta and variance equal to k x transpose x inverse k transpose times sigma squared. Now I can construct a chi-squared out of k beta hat very easily. So let's take k beta hat minus k beta minus its mean transposed, and then simply times the inverse of its variance matrix, k x transpose x inverse k transpose inverse times k beta hat minus k beta. And that's clearly going to be chi-squared rank of k. And the reason being that this, by virtue of k being a full row rank matrix, is going to be an invertible matrix. And this is k by whatever the number of rows of k is, that by that square matrix. And just by the results from the first section of this chapter, we have that this is exactly chi-squared. Furthermore, the only thing random in this chi-squared is beta hat. And we know that this is independent of s squared. So what I could do is take this quantity, divide it by its degrees of freedom, let's just say rank of k, and then divide it by n minus p s squared over n minus p sigma squared. And oh, I realized I made a mistake. I forgot my sigma squared right there. I just reminded myself of this. Okay, and the reason I remembered it is because now when I divided these two things out, I have a chi-squared rank of k in the numerator, and I have a chi-squared n minus p in the denominator, and they're independent because in the numerator, the only random thing is beta hat. In the denominator, s squared is just a function of the residuals e, so the numerator is independent of the denominator, and what I've done is taken a chi-squared divided by its degrees of freedom, and then divided by another chi-squared, an independent chi-squared divided by its degrees of freedom. The sigma squareds, of course, will cancel out, and that's why I remembered that I forgot my sigma squared from above. So, and then these n minus p's, of course, cancel out. So this statistic right here, which I can just move this s squared up right into the denominator, that statistic right there is the f-test for a general linear hypothesis. The most clear one would be a matrix K that grabs all of the coefficients except for the intercept, for example. And that is the standard f-test from that our linear regression model puts out. But I hope you can see that this is a pretty easy result to prove now that we have all this machinery under our belt.